Hello everyone, welcome to the course CS22032 Deep Neural Networks. My name is J. Lavanya and I am an assistant professor in the Computer Science and Engineering Department at Sri Venkateshwara College of Engineering. In this course, we will learn about deep neural networks, which are a special type of artificial intelligence that helps machines learn from data. These networks are used in many real-world applications like face recognition, voice assistance, self-driving cars, and medical diagnosis. This presentation will give you an introduction to the basics of deep neural networks, how they are built, how they learn, and where they are used. So let's get started. Unit 1, Introduction to Neural Networks. So in this unit, we will start with linear regression, a fundamental technique used to predict continuous outcomes based on input variables. Next, we will explore logistic regressions, which is widely used for classification tasks, particularly when the goal is to categorize the data into two distinct classes. Following that, we will discuss the concept of the loss function and the cost function. These functions are helps us to measure the error in our predictions and guide the optimization of our models. We will also study softmax regression, an extension of logistic regression designed for multi-class classification problems. Finally, we will cover model evaluation, where we will learn how to assess the performance and effectiveness of our models using various evaluation metrics.
So first, what is regression in neural networks? A regression neural network model takes the input features and processes them through multiple layers to produce a numerical prediction. For example, if the input features are the size of the house, number of rooms, and the zip code, the model's output could be the predicted price of the house. Using these input values, we will predict the output like price of the house, and this differs from the classification task. So where the output is a category or a class label, such as identifying an image as a cat or a dog. In regression problem, the outputs are continuous real valued numbers rather than as discrete labels. So in regression, the outputs are real valued numbers. Fundamental components of neural networks. In this we will see four layers. First one is input layer, second one is hidden layer, and third one is activation layer, and then final is output layer. First, input layer. The input layer is responsible for receiving the input features. Each neuron in this layer corresponds to one feature in the training data. For example, if your data has a features such as age, height, and weight, there will be three neurons in the input layer. And then second one is hidden layers. The hidden layers performs non-linear transformation on the input they receive. These layers can extract important features and patterns that help the network learn complex relationships. The number of hidden layers and the number of neurons in this layer define the architecture of the model. Each neuron in one layer is connected to neurons in the next layer through a matrix of weights which are adjusted during training. And the third one is activation functions. Activation functions introduce non-linearity into the neural network. This non-linearity allows the model to learn and represent complex relationships within the data, which in which the linear functions alone cannot capture. So the common activity functions include ReLU, which is described as a rectified linear unit, tanh, hyperbolic tangent, and sigmoid. Each of these functions has its own characteristics and applications, but all serve the essential purpose of enabling the network to model the patterns. And the last one is output layer. The output layer produces the final result of the network's computation. In this regression task, this layer contains a single neuron that outputs a continuous value such as predicted price, temperature, or any other numerical quantity. This output represents the network's prediction based on the input features and the learned parameters. And finally, understanding these components is the key to designing effective neural networks to a specific prediction tasks.
Next, the components of neural networks, we have neurons, also called as a nodes. These are the basic processing units of the network. Each neuron takes one or more inputs, multiples them by weights, adds a bias, passes the result through an activation function, and produces an output. You can think of each neuron as a small decision maker contributing to the final prediction. Next, we have the connections or edges. These connections like neurons from one layer to the next, and they carry information forward through the network. Each connection has a weight that determines how strongly the signal from one neuron influences the next. Finally, we have weights and biases. The learnable parameters of the model. The weights represents the strength of the connections between neurons. During training, these weights are adjusted so the network can better map inputs to outputs. Biases act like adjustable offsets, helping shift the activation function and allowing the network to learn more flexible patterns. Together, neurons, connections, weights, and biases form the core structure of any neural network. So next one is activation function. Activation function plays a very important role in neural networks. Their main purpose is to introduce non-linearity into the model. Without them, a neural network would be have just like simple linear model and it wouldn't be able to learn complex patterns or relationships in data. Some of the most widely used activation functions include sigmoid, which squashes values between 0 and 1, making it useful for binary classification. ReLU, which is the most popular today, allows positive value to pass through while blocking negative ones. This makes training faster and more efficient. TANH, which outputs values between -1 and +1 and is often used when data is centered around 0, and softmax, which is used at the output layer for multi-class classification, since it converts raw scores into probabilities. Overall, activation function helps the network understand nonlinear structures and allow it to make more accurate predictions. Propagation functions. Propagation functions, which defines how information flows inside the neural network. There are two key processes involved. The first is forward propagation. So here the input data moves layer by layer through the network. Each layer applies weights, biases, and activation functions to transform the information until we reach the final output. The second process is backpropagation, which is responsible for learning. After making a prediction, the network compares it with the actual target value and calculates the error. Backpropagation then converts backwards through the layers, computing gradients that tell the network how much each weight contributed to that error. This information is used to update the weights during training. Together, forward propagation handles prediction while back propagation handles correction and learning. Next one is a learning rule or optimization algorithm. A learning rule, also called an optimization algorithm, determines how the network updates its weights and biases during training. The goal is to minimize the error between predicted and actual values. The most basic optimization method is gradient descent, where the model moves step by step in the direction that reduces the loss. Then we have more advanced optimizer like Adam, which combines momentum and adaptive learning rates, making training faster and more stable. Another popular one is RMS Prop, which adjusts the learning rate for each parameter and works very well for recurrent and deep networks. In simple terms, the learning rule which decides how quickly and how effectively the network learns from its mistakes.
Okay, so this is the architecture of neural network. This neural network contains the architecture of neural network contains three layers, three primary types of layers. First one is input layer, hidden layer, and then hidden layer, and then output layer. In input layer, this is the first layer of the network which receives the raw input features, input data from the user. So each square in the diagram represents a neuron corresponds to an input features. This yellow square represents the input features. The input layer passes the data to the next layer for further processing. And then second one is a hidden layer. Here we have two hidden layers. The input layers are transformed the data to the hidden layer and represented here by the blue circles. These layers perform complex transformations on the data by applying weights and activation functions. Each neuron in the hidden layer is connected to every neuron in the previous and subsequent layers, allowing the network to learn the predictive patterns. And then last layer is output layer. The network produces its prediction through the output layer depicted by the green circles. In this regression task, this layer typically contains one or more neurons that outputs the continuous values. The connections between neurons represented by the arrows indicated the flow of information and application of weights. During training, those weights are adjusted to minimize the error between the predicted and actual classes. And this is the overall architecture of the deep neural networks. Regression. So the regression problem arises whenever we want to predict a numerical value. Regression refers to a set of methods used to model the relationship between input data points, which is denoted as x, and their corresponding real valued target and which is denoted as the y. For example, regression techniques are commonly applied to predict the prices such as homes or stock estimations, and to estimate the length of the hospital stays for the patients in hospitals, and to forecast demand in retail sales, and also many other applications. It is important to note that not every prediction problems falls under classic regression. In this upcoming sections, we will explore the classification problems where the objectives is to predict the categorical membership rather than the continuous numerical values.
Why regression matters. Regression is one of the important tools in data analysis and machine learning because it helps us predict and understand real world patterns. First, regression is widely used for forecasting trends, whether we want to predict future sales, estimate customer demand, or analyze stock price movements. Regression, which helps us to look ahead based on past idea. This makes it essential for planning and strategic decision making. Second, regression supports critical decisions in fields like business, healthcare, and engineering. For example, hospitals can predict patient volume Companies can estimate production needs and engineers can model system behavior. Accurate predictions allow organizations to allocate resources more efficiently. Finally, regression provides valuable insight into how variables are related. For instance, in real estate, regression can show how factors like square footage, location, or number of rooms influence a house price. Understanding these relationships helps the experts to make better judgment and uncover what truly impacts outcomes. So overall, regression matters because it helps us to predict the future, make informed decision, and understand the factors that shape our result. Types of regression. Regression comes in several forms depending on the type of relationship we want to model. Let's look at three of the most commonly used types. First, linear regression. This is the simplest form where we assume a straight line relationship between the input variable and the output. Its equation is y equal to beta naught plus b1x plus summation. We will call it as epsilon, where b naught is the intercept, beta 1 is the slope, and epsilon represents the error. So linear regression is easy to interpret and widely used for basic predictions. Next is multiple linear regression. Here, instead of using just one input variable, we can use multiple predictors. For example, predicting the price of a house may depend on its size, location, age, and other features. This helps us model more realistic scenario where many factors contribute to the final outcome. Finally, polynomial regression. Sometimes the relationship between variables is not a straight line. In such cases, polynomial regression helps by adding higher order terms like x square or x cube. This allows the model to fit curved patterns and capture more complex trends in the data. Together, these types of regression gives us flexibility to model simple, multi-factor and non-linear relationships depending on the problem we are solving. Next, logistic regression. So, logistic regression and advanced regression methods. Although logistic regression is technically a classification algorithm, it's usually taught alongside regression because of how similar the structure is. But instead of predicting a continuous value, logistic regression predicts the probability of a categorical outcome. For example, it can estimate whether a customer will buy or not buy a product or whether a tumor is benign or malignant, and it uses the sigmoid function to squeeze outputs between 0 and 1, making it ideal for probability-based decisions. Now, moving to more advanced regression techniques, we have methods like ridge, lasso, and elastic net. These are known as regularization techniques, and their main purpose is to prevent overfitting. Ridge regression penalizes large weights. Lasso can actually shrink some coefficients to zero, effectively performing future selection, and the elastic net, which combines both approaches to balance stability and sparsity. We also have nonlinear regression methods, which are useful when relationships can't be captured with straight or curved equations. Models such as decision trees or neural networks can learn complex nonlinear patterns by splitting data or using layered transformations. These models are powerful when dealing with real world problems where patterns are rarely purely linear. Overall, these advanced metrics help us handle complex data, reduce overfitting, and improve prediction accuracy in a wide range of applications. Application of regression. So, regression is one of the most widely used predictive tools across industries because it helps convert historical data into actionable insights. In business, regression is used for things like sales forecasting, helping companies estimate future demand and plan inventory. It is also used for pricing models where business analyze how factors like competition, seasonality, or product features influence price. In healthcare, regression supports critical decisions such as predicting patient recovery time, estimating hospital stay duration, or modeling disease progression. These predictions help doctors plan treatments more efficiently and improve patients' outcomes. In finance, regression is a core technique for stock price prediction, and risk modeling. Financial analysts use it to understand market trends, assess portfolio risk, and forecast economic indicators. In engineering field, regression plays a major role in demand and load forecasting, such as predicting electricity usage or system loads. It is also used for perform the optimization, where engineers analyze how different variables affect efficiency or reliability. Overall, the regression is incredibly valuable because it helps organizations forecast the future, optimize decisions, and better understand the factors that influence key outcomes. Linear regression. So, linear regression is one of the most fundamental and widely used supervised algorithms, especially when our goal is to predict continuous numeric values. The idea is simple but extremely powerful. We try to fit a straight line, but best represents the relationship between the input variable, which we call x, and the output variable, which we call y. This line is not chosen randomly. It is mathematically calculated in a way that minimizes the error between the predicted value and the actual value in the dataset. By doing this, linear regression provides a clear way to understand how much y changes when x changes. One of the reasons this method is so popular is its interpretability. So we can look at the model's equation and understand exactly how each feature influences the result. This makes it extremely useful not only in machine learning but also in traditional statistics, economics, marketing, healthcare, and many scientific fields. Another reason linear regression is widely used because it is simple and computationally efficient. It trains very quickly, even on large datasets, and it does not require complex tuning. Despite its simplicity, it often provides surprisingly strong performance when the underlying relationship between variables is linear or close to linear. So, linear regression helps us to predict continuous outcomes, understand the relationship between variables, and make informed decisions, all through the elegant idea of fitting a straight line to data. The main objective of linear regression. So it is to find the best fitting line that represents the relationship between the input variable x and the output variable y. This line should pass as close as possible to all the data points so that it accurately captures the underlying trend. The equation of this line is written as y equal to mx plus c, where m represents the slope of the line and c represents the intercept. The slope tells us how much y changes for every unit change in x, and the intercept tells us the value of y when x is 0. To find this line, the model focuses on reducing the differences between the predicted value and the actual values. This difference or error is measured using a cost function, usually mean squared error. So the ultimate goal of linear regression is simple. Minimize prediction error by choosing M and C in such a way that the line fits the data as accurately as possible. This makes the model reliable for making future prediction based on past observations.
Linear regression. So before going to the linear regression, we will know the terminology of learning, machine learning, the data set. So data set here is called as a training data set or training set. We can use to train a model is referred as a training data set or simply training set. Each row within the data set which typically corresponds to a single observation or record, such as the details of one sale is called as an example. It may also be referred as a data instance, data point or sample. The value we aim to predict for an instance is the price of the house is known as label or target. The variable used to make this prediction, such as age or area in this case, are known as features or covariates. These features serve as the input to the model and play a crucial role in determining the output. In most cases, we use the symbol n to represent the number of examples or data points in our dataset. Each data instance is typically indexed by I, where I ranges from 1 to n. The input features of the I, which are, for example, we are denoted as a x of I, and the corresponding label or targeted value is represented by y of I. The input feature is here x of I and the target value is the output is y of I. This notation allows us to clearly define the structure of the dataset where each pair x of I and then y of I represents one complete training example for an input and its associated output. The linearity assumption says that the target variable such as price can be expressed as a weighted sum of the input features such as area and then age. In this equation, the terms W area and W age, which represents the weights which determine the relative importance of each features. The term B is the bias, also referred to as the intercept. The bias which allows our model to make accurate prediction even when all the features have the value of 0. Thus, it increases the flexibility and expressiveness of the model. The main objective in training such a model is to determine the optimal values for the weights and bias such that weights and bias that the model's predictions closely align with the actual target values observed in our dataset. This is typically achieved by minimizing the loss function, most commonly the mean squared error, which penalizes the large deviations between predicted and actual values.
So linear regression comes in two major forms depending on how many input variables we use. So first we have simple linear regression. This type uses only one input variable to predict the output. The goal is to fit a straight line to the data showing how a single factor influences the result. For example, predicting house price based solely on square footage is a classic case of a simple linear regression. It is easy to interpret and is often the starting point for understanding regression concepts. Next, we have multiple linear regression. In real-world problems, outcomes are rarely determined by just one factor. Multiple linear regression addresses this by using several input variables at the same time. Here, the model learns how multiple factors such as size, location, age, and number of rooms combine to influence the output. This makes the predictions more accurate and the model more realistic for complex data sets. Simple linear regression focuses on a one-to-one relationship, while multiple linear regression captures the effect of multiple predictors working together to determine the output. Next one is polynomial regression. So polynomial regression and regularized linear models. Now moving forward, let's talk about the two important categories of regression that helps us dealing with more complex data sets. So polynomial regression is essentially a high non-linear extension of linear regression. Instead of using only the original input x, we include higher degree terms such as x square, x cube, and even higher powers if needed. These extra terms allow the model to fit curved patterns in the data rather than just straight lines. The interesting part is that even though it models nonlinear relationships, it is still considered a linear model because the parameters, the coefficients we learn remain linear in form. This makes it both flexible and computationally manageable. The second category is regularized linear models, which helps us handle overfitting, especially when we have many features or noisy data. The idea is to add a penalty term to the cost function so the model does not rely too heavily on any one coefficient. There are three major types: ridge regression, lasso regression, and elastic net. So, ridge regression, which uses a L2 penalty. This shrinks the coefficient but never drives in them completely to zero. Lasso regression. Lasso regression, which uses an L1 penalty. This can shrink some coefficients exactly to zero, efficiently performing future selections. Elastic net, which combines both L1 and L2 penalties, giving us a balance between ridge stability and lasso sparsity. Together, these regularized models make our predictions more robust and help avoid overfitting in real-world scenarios where data can be messy or high dimensional.
Assumptions of linear regression. To ensure that linear regression gives trustworthy and accurate results, there are a few important assumptions that the data should satisfy. These assumptions help the model behave as expected and make the predictions reliable. The first assumption is linearity. This means the relationship between the input variable x and the output variable y should be roughly linear. In other words, changes in x should lead to proportional changes in y. The second assumption is independence of errors. The errors or residuals, the difference between the actual and predicted values, should not be correlated with each other. If errors follow a pattern, it means the model is missing important information. The third assumption is homoscedasticity. So this means the variance of the errors should remain constant across all levels of x. If the spread of error gets larger or smaller for certain values, it indicates heteroscedasticity, which can weaken the model's reliability. The fourth assumption is normality of residuals. The residuals should follow a normal distribution. This is especially important for generating confidence intervals, hypothesis test, and proper statistical interpretation of the model. And finally, the fifth assumption is no multicollinearity. So it applies to multiple linear regression. The predictor variables should not be overly correlated with each other. If two features contains very similar information, the model becomes unstable and the coefficient becomes unreliable. If these assumptions hold true, the linear regressions provide strong, interpretable, and accurate results. Evaluation of linear regression model. To understand how well our linear regression model is performing, we use a set of evaluation metrics that measure accuracy, error, and overall fit. The first important metric is the R-square. R-square. It is also known as the coefficient of determination. R-square tells us how much of the variation in the output variable is explained by the model. In simple terms, a higher R-square means when the model is doing a better job at capturing the underlying pattern in the data. The formula is r square equal to 1 minus sum of squared errors to the total sum of squares. If the model's predictions are close to the actual values, the numerator becomes small and r squares moves closer to 1. So r square gives us a quick way to judge overall model quality. So the second matrix is adjusted r square. While r square works well for simple data sets, it can be misleading when we add more features. Adjusted r square solves this by penalizing the model for unnecessary predictors. This makes it a more reliable metric for evaluating models with multiple input variables. Next, we use a group of metrics called error metrics, which tells us how far off our predictions are from the actual values. MAE, or mean absolute error, gives the average of absolute differences between predicted and true values. It's simple and interpretable. So MSE, or M squared error, squares the differences, giving more weight to large errors. This helps highlighting big mistakes. So next one is RMSE, root mean squared error. It is just the square root of MSE. It has the same units as the target variable, making it easier to understand. Together, these metrics help us to evaluate accuracy, stability, and prediction quality, giving us a complete picture of how well our linear regression model is performing. Evaluation metrics of linear regression. To understand how well a linear regression model is performing, we use several evaluation metrics. These help us to judge how accurate the predictions are and how well the model fits the data. The first metric is the R square score. R square measures how much of the variance in the output variable y is explained by the model. The formula is R square equal to 1 minus SSE by SST, where SSE is the sum of squared errors and SST is the total sum of squares. If R square is 1, the model perfectly explains the data. If R square is 0, the model explains nothing. It is no better than simply using the average of y. And if R square becomes negative, it means the model is actually worse than the baseline prediction. The second metric is adjusted R square. This becomes especially important when we add multiple features. R square always increases when new variables are added, even if those variables are not useful. Adjusted R square corrects this by penalizing unnecessary predictors. Its formula is adjusted R square equal to 1 minus R square into n minus 1 by n minus k minus 1. Where n is the number of samples and k is the number of predictors. This makes adjusted R square a much more honest indicator of model performance in multi-feature datasets. Finally, we look at the error-based metrics like RMSE and MAE. These numbers tells us how far our predictions are from the actual values in real units, which makes them very easy to interpret. MAE gives the average absolute error. So RMSE, the squared root of the mean squared error, which penalizes large mistakes more heavily. Together, these metrics gives us a complete picture of how good our regression model really is, whether it fits the data well, and how accurate its predictions are. Advantages of linear regression. Linear regression has several key advantages that make it one of the most widely used algorithms in machine learning and statistics. First, it is simple and fast. The mathematical model is straightforward and it trains quickly even on large data sets. Second, it works efficiently on large data sets because the computations are not complex. Linear regressions can handle thousands or even millions of data points without much difficulty. Third, the coefficients are easy to interpret. We can directly see how each input variable affects the output, which is especially useful in fields where understanding relationships is as important as making predictions. Fourth, it serves as a good baseline model. Even if we later move to more complex algorithms, linear regression provides a solid starting point to benchmark performance. Finally, it works well for linearly separable data. When the relationship between the input and output is roughly linear, linear regression can produce highly accurate predictions with minimal effort. Overall, linear regression combines simplicity, interpretability, and efficiency, making it a practical choice for making predictive tasks. Limitations of linear regression. While linear regression is simple and widely used, it does not have several limitations that we should be aware of. First, it cannot capture non-linear relationships. If the underlying relationship between the input and output variable is not linear, a straight line model will fail to represent the data accurately. Second, it is highly sensitive to outliers. Extreme values can disproportionately influence the slope and intercept, leading to poor predictions. Third, performance decreases in the presence of multicollinearity. When predictor variables are highly correlated with each other, the model struggles to determine the individual effect of each features, which makes the coefficients unstable. Fourth, linear regressions assumes linearity. These assumptions may not always hold in real-world data, limiting the applicability of the model. Finally, it is prone to overfitting when there are many irrelevant or noisy variables, including too many features that do not contribute to the target, that can reduce model performance and generalization. Overall, while a linear regression is powerful and interpretable, it's important to check these limitations before applying it to real-world problems. Applications of linear regression. So real world applications linear regression is widely used across industries because it provides a simple yet effective way to make predictions and understand relationship between the variables. First, it is used in real estate, for example, predicting house prices based on features like size, location, and number of rooms. Second, in business, linear regression helps in estimating sales or revenue, allowing companies to plan inventory, budgets, and growth strategies. Third, it is applied in environmental science such as temperature or climate modeling, where we can predict trends based on historical data. Fourth, in healthcare, linear regression can predict medical parameters like blood sugar levels or patient recovery times, aiding in better treatment planning. Fifth, in finance, it is used for risk scoring, credit evaluation, and investment forecasting, helping organizations make informed financial decisions. Sixth, in operations and supply chains, linear regressions support demand forecasting, enabling efficient resource allocation. Finally, in marketing, it helps to measure advertising effectiveness by quantifying how different factors influence customer response or sales. Overall, the linear regression is versatile, interpretable, and provides actionable insights in almost any domain where relationships between variables need to understood or predicted. When our data contains D features, the model prediction denoted as y cap can be expressed as y cap equal to w1 x1 plus w2 x2 plus w3 x3 plus up to wd xd plus b. Here b is the bias or intercept, w1 is the weightage of the input feature, and x1 is the activation function what we applied to predict the value. This formulation can be compactly written using vector notation, where we group all features into a vector x and all weights into a vector w. This leads us to the more elegant way representation for y cap equal to w transpose of x plus b. Here the vector x corresponds to a single data point, and w transpose of x denotes the dot product between the weight and future vectors, which means the multiplication of weight and the activation function. When we consider the entire data set, we often refer to the design matrix denoted as X, where each row in represents one example and each column corresponds to a feature. Logistic regression. So in first unit, the second topic is logistic regression. Logistic regression is a fundamental classification method in machine learning, and it is specifically identified as a special case of softmax regression, specifically for the scenarios in which the objective is to distinguish between exactly the two distinct classes. In this, we consider the underlying data distributions denoted by P of x and Q of x, and the logistic regression serves as a statistical tool for determining from which of these two distributions of a particular observation is likely to be originated. In this approach, it proves especially powerful when the goal is not merely to classify but to do so in a probabilistic interpretable manner. Logistic regression does not simply assign a label to an input. It estimates the probability that the input belongs to a particular class. This probabilistic output enables practitioners to apply thresholds, assess risk, and make decisions under uncertainty, and invaluable features in the fields such as medicine, finance, and policy making.
Why not use linear regression for classification? So let's talk about why linear regression is not the right choice for classification problem. First is output range problem. So linear regression is designed to predict continuous values. Its outputs can range anywhere from negative infinity to positive infinity. But classification tasks like predicting whether an email is a spam or not, which requires outputs between 0 and 1, because we are dealing with probabilities. Linear regression may simply does not respect this boundary. Second one is predictions outside 0 and 1. As a result, predictions can fall below 0 or above 1. Imagine predicting that a patient has a probability of minus 20% of having a disease or 150% chance of being admitted. These values make no sense in classification context. Third one is error function becomes non-convex. Another issue is the error function. In regression, we minimize squared errors which work well for continuous outputs. But when applied to classification, the error surface becomes more non-convex. This means optimization is harder and the model may not converge to a useful solution. Sensitivity to outliers. Linear regression is also highly sensitive to outliers. A single extreme data point can distort the regression line. In classification problems, this can lead to misclassify entire groups of data because the model is pulled in the wrong direction. Fifth one is poor handling of decision boundary. So most importantly, linear regression cannot properly handle classification boundaries. Classification is about separating classes, drawing a line between yes and no, or a spam and not spam. So linear regression does not naturally create these boundaries. Instead, it tries to fit a continuous line which does not capture the discrete nature of classification. The need for probabilistic models. So therefore, we need models that outputs probabilities. Logistic regression, for example, uh, it uses the sigmoid function to squash outputs into a range between 0 and 1. This makes predictions interpretable as probabilities and allows the model to define clear decision boundaries. So, while linear regression is powerful for predicting continuous outcomes, it fails when applied to classification. So the problems include outputs outside the valid range, non-convex error functions, sensitivity to outliers, and poor handling of boundaries. That's why we turn to models like logistic regression, which are specifically designed for classification tasks. Logistic regression model. So it is one of the most widely used models for classification. Purpose of logistic regression. So, unlike linear regression, which predicts the continuous values, logistic regression predicts the probability that an output belongs to a particular class, usually class 1. In other words, it answers the questions what is the probability that y equals 1 given x. Second one is probability expression. So, mathematically, we write this as P of y equal to 1 modulo x equal to hat of y. Here, hat of y which represents the predicted probability. Third, the range problem. So, but here's the challenge. Both probabilities must always lies between 0 and 1. Linear regression outputs values anywhere from negative infinity to positive infinity, which does not make sense for probabilities. Fourth one is the sigmoid function. To solve this, logistic regression uses the sigmoid function. The sigmoid takes any real number as input and squashes it into a value between 0 and 1. So the formula is sigma of x equal to fraction of 1 divided by 1 plus e to the power of minus z. This curve is S-shaped and smoothly transitioning from 0 to 1. When z is very negative, the output approaches to 0. When z is very positive, the output approaches to 1. Fifth one is interpretation. So this means the model can now output valid probabilities. So sixth and next one is decision boundary. Finally, we set a threshold often zero point 0.5 if the predicated probability is greater than zero point 0.5. So decision boundary. So decision boundary in logistic regression. First, after computing the probability that a sample belongs to positive class using the sigmoid function, so here the equation is y cap equal to sigma of z. So we classify it as class 1 class 1 if y is greater than or equal to zero point 0.5 and class 0 if y cap is less than or equal less than zero point 0.5. The decision boundary is the set of points where the model is uncertain, that is when a y cap equal to zero point 0.5 for two futures, this is given by W1 x1 plus W2 x2 plus B equal to 0. So with the original futures, the decision boundary is linear. However, if we use polynomial or other nonlinear futures, the boundary can become nonlinear, which allows the model to separate more complex patterns in the data. Training logistic regression using gradient descent. So we train the logistic regression model while we updating the weights using gradient descent, just like in a linear regression. The update rule for each weight Wj is Wj equal to Wj minus alpha of dou j by dou Wj. Here, alpha is the learning rate and dou j by dou wj is the derivative of the loss function with respect to the weight. The main difference from linear regression is that in logistic regression, our predictions pass through the sigmoid function. This means the derivative accounts for the sigmoid, but the overall idea remains the same. We move the weights in the direction that reduces the loss. So in short, logistic regression training is in iteratively adjusting weights through gradient descent using the probability based predictions from the sigmoid functions to guide the updates. Types of logistic regression. So first one is a binary regression, binary logistic regression. As the name suggests, this model is used to predict two possible classes, either 0 or 1. So common examples include, first one is medical diagnosis, predicting whether a tumor is malignant or benign. And second is email filtering, classifying emails as a spam or not spam. and for admissions are predicting whether a student will be admitted or not. So binary logistic regression outputs a probability between 0 and 1, which we then convert to one of the two classes using a threshold, typically 2.0.5. So whenever the outcome has only two possible categories, so binary logistic regression is the go-to model. So next one is multinomial logistic regression. So in multinomial logistic regression, this is an extension of logistic regression which used when we need to predict more than two classes. Instead of using the sigmoid function, multinomial logistic regression uses the softmax function, which converts the output into probabilities that sum to 1 across all classes. Some common examples include digit classification, where the model predicts digits from 0 to 9. The well-known data set where the goal is to classify flowers into three different species. So, multinomial logistic regression is ideal when the target value involves multiple categories, and softmax helps the model decide which class is the most probable. Third one is ordinal logistic regression. So in this type of logistic regression is used when the output classes are ordered, meaning the categories follow a natural ranking, even though the differences between them may not be equal. So a simple example is a rating scale such as poor, average, good, excellent. Here, the categories clearly have an order, and an ordinal logistic regression is designed to capture this structured progression. So, whenever our target labels follow a meaningful sequence, ordinal logistic regression is the appropriate choice. Regularized logistic regression. So, in regularized logistic regression, it helps to prevent the model from overfitting. To control overfitting, we add a penalty term to the loss function. The two most common types are L2 regularization, L1 regularization. So, in L2 regularization, we'll also called as a ridge. So, it can be defined as lambda summation of Wi the whole square. And L1 regularization, we also called as a lasso. It is also called as lambda summation of modulus of Wi. So L2 discourages large weights by pushing them towards zero smoothly. L1 forces some weights to become exactly zero. These penalties have different effects. So L1 performs a feature selection because it drives some weights to zero, effectively removing irrelevant features. L2 keeps all weights small but never exactly zero, making the model more stable and preventing extreme parameter values. So regularization not only prevents overfitting but also can help simplify the model and improve generalization. Assumptions of logistic regression. So, the key assumption of logistic regression, it helps to ensure that the model perform reliably and that the results are meaningful. Independent samples. Each data point should be independent of the others. If samples influence each other, the model's estimates can become biased. So, second one is the linear relationship in log odds. So the log odds of the outcomes should have a linear relationship with the input features. This does not mean the probability is linear, only the log odds. No or minimal multi-collinearity. So the features should not be highly correlated with each other. High multi-collinearity makes the model unstable and the coefficients reliable. Fourth one is large sample size. Logistic regression uses maximum likelihood estimation, which performs much better with large data sets. Small data sets can lead to inaccurate or unstable estimates. Fifth one is the feature scaling. Scaling the features is not mathematically required, but it greatly improves the speed and stability of gradient descent during training. These assumptions ensure that logistic regression works efficiently and produces trustworthy predictions. Metrics to evaluate logistic regression. Uh, so first one is accuracy. For classes, it is classification. First one is accuracy. So accuracy measures how many predictions the model got correct overall. So it is defined as accuracy equal to TP plus TN that divided by TP plus TN plus FP plus FN. While accuracy is simple and useful, it may be misleading imbalanced data sets. So second one is the precision, recall, and F1 score. These metrics give a deeper understanding of model performance. So precision tells us out of all the samples predicted as positive, how many were actually positive. It focuses on correctness of positive predictions. Recall tells us out of all actual positives, how many did the model correctly detect. It measures how well the model catches the positive class. F1 score is the harmonic mean of precision and recall. It provides a balanced score when we need to consider both false positive and false negative. These metrics are especially important when dealing with imbalanced datasets where accuracy alone may not reflect true model performance. So next one in evaluating logistic regression is confusion matrix, ROC curve and AUC. So in this, it is the most important evaluation tool for logistic regression. It gives a complete picture of how the model performed. It shows the four key outcomes, true positive, true negative, false positive, false negative. So true positive, it correctly predicates the positives, and a true negative, which means correctly predicates negatives, and it false positive predicted positive but actually negative, and false positive predicted negative but actually positive. So this matrix helps us to understand not just how often the model is correct, but where it makes mistake. And ROC curve and AUC. So the ROC curve plots the true positive rate against the false positive rate at different probability thresholds. It helps us to analyze how well the model separates the two classes. The AUC, or area under the curve, summarizes the ROC curve into a single number. An AUC close to 1 indicates an excellent model. An AUC of zero point 0.5 means the model is no better than random guessing. So ROC to AUC is extremely useful for comparing models and evaluating performance beyond just accuracy. Strengths of logistic regression. First, it is a simple, fast, and computationally efficient. Training is very quick, even on large data sets, which makes it suitable for real-time or low-resource applications. Second, logistic regression requires relatively less data compared to more complex models like deep learning. It works well even when the data is not extremely large. Another major disadvantage is that it outputs actual probability values, not just class labels. This makes it very useful in fields like medicine or finance, where understanding the confidence of a prediction is important. It also has interpretable coefficients. We can easily understand how each feature affects the log odds of the outcome, making the model transparent and explainable. Finally, logistic regression is an excellent baseline model for classification tasks. It's often the first model we try before moving on to more complex approaches. Then limitations of logistic regression. First, it only works well for problems that have roughly linear decision boundary. If the relationship between the features and the classes is highly non-linear, the model will struggle unless we manually add future transformations. Second, it is not suitable for very complex or highly nonlinear datasets. More advanced models like decision trees, random forest, or neural networks handle such patterns much better. Third, logistic regression is sensitive to outliers. Just a few extreme values and can distort the model's coefficient and reduce performance. And finally, logistic regression cannot automatically detect future interaction. If interactions between variables are important, we must explicitly create those interaction terms ourselves. So while logistic regression is simple and effective, it does have clear limitations, especially for complex or non-linear real-world data. These are the real-world applications using a linear logistic regression. So first one is the email detection, spam detection. So it helps us to classify incoming emails as either spam or not spam based on their content and metadata. And in healthcare, it is used for a disease diagnosis, such as predicting whether a patient has cancer, diabetics, or other medical conditions based on clinical features. And it is also used in credit card fraud detection, where the model predicts whether a transaction is fraudulent or genuine. Another important application is customer crunch churn prediction, helping companies identify whether the customers are likely to leave so they can take preventive actions. And logistic regression also works well for sentiment classification, such as determining whether a review is positive or negative. And in many hospitals, it is used for medical risk prediction, like estimating a patient's risk of complications or mortality. These examples shows how logistic regression is simple yet powerful across many different domains.